Hi guys, this is A2 Chemistry, Transition Elements, and we are looking at orbital splitting in complexes. Question 1. Although the 5d orbitals are at the same energy in an isolated atom, when a transition element ion is in an octahedral complex, the orbitals are split into two groups. Draw an orbital energy diagram to show this, indicating the number of orbitals in each group. So, in an isolated ion, we've got all the 5d orbitals having equal energy, and in an octahedral complex, we've got them splitting into two groups with the orbitals along the axis having a higher energy than the orbital present between the axes. Labeling the orbitals, we have dxy, dxz, dyz here, followed by dx square, y square, and dz square. In the octahedral complex, we've got dx square, y square, and dz square present in the higher set of d orbitals, and we have got dxy, dyz, and dxz present in the lower set of d orbitals. However, both of them at a higher energy than in the isolated transition metal ion, with an energy gap between them labeled as delta E for the energy difference and O to represent the octahedral complex energy difference. Question 2. In a free gas phase transition metal ion, the d orbitals all have the same energy, but when the ion is in a complex, the orbitals are split into two energy levels. Explain why this happens. So, the electrons present in the d orbitals are repelled by the lone pairs of electrons of the approaching ligands, and the ones closer to the ligands are repelled more than the ones in the orbitals further away, forming two sets of d orbitals. So that is how the splitting of d orbital occurs when the ligands approach the central transition metal ion. How does this splitting help to explain why transition metal complexes are often colored? So, the energy gap corresponds to the visible region of the electromagnetic spectrum. When light falls on the complex, an electron from the lower set absorbs it and moves to the higher set. color complementary to the wavelength of light absorbed is observed. And that is how orbital splitting helps to explain why transition metal complexes are often colored. Next, why does the color of a transition metal complex depend on the nature of the ligands surrounding the transition metal ion? Because different ligands cause different sizes of energy gaps. The smaller the gap, the lighter the color, and the larger the gap, the deeper the color observed. And that is how colors of transition metal ions are dependent on the ligands which bind to them. Question 3. The presence of electrons in d orbitals is responsible for the color of transition element compounds. The d orbital in an isolated transition metal atom or ion are all at the same energy level. What term is used to describe orbitals that are at the same energy level? So the term used to describe them are degenerate d orbitals. Next, the complete the diagram to show the splitting of the d orbital energy levels in an octahedral complex ion. So the two d orbitals that are along the axis have a higher energy than the three d orbitals that are present between the axes. So these would be dx square y square in the higher set and dz square in the higher set, whereas dxy, dyz, and dxz are the orbitals present in the lower set in an octahedral complex. Question 4. In an isolated transition metal atom, the 5d orbitals have the same energy. When a transition metal ion forms a tetrahedral complex, the d orbitals are split into two groups of different energies. Complete an orbital energy diagram to show this, indicating the number of orbitals in each group. So we need to draw the configuration of the d orbitals in two sets in a tetrahedral complex. So the ligands in a tetrahedral complex approach between the axes. So the ones between the axes are promoted to a higher energy level as compared to the ones along the axis which are also promoted to a higher energy level but below the set with the three orbitals that are present between the axes. So these orbitals would be dxy, dyz, and dxz in the higher set, and the dx square y square orbital and the dz square orbital in the lower set with an energy gap between them that will be labeled as delta E, and we include a T for tetrahedral complex. Question 5. Complete the electronic configuration of the iron atom. So the atomic number of iron is 26. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. In some of its complexes, Fe3 plus ion has only one unpaired electrons in its d orbitals. Using the symbols up arrow and down arrow to represent electrons of opposite spins, complete the following diagram to show the d orbital electronic configuration of this Fe3 plus ion. So Fe3 plus ion would lose 3 electrons, therefore its d orbital configuration would be 3d5. In a normal Fe3 plus ion, the configuration would be each of the d orbitals being occupied by a single electron. However, this statement says that it only has one unpaired electron in its d orbital. So, for that reason, we will have one of each electrons present in the lower set and none in the higher set. And we would have two of the electrons in the lower sets pairing up based on the statement given in this question. So this would leave only one unpaired electron in the d orbital. Question 6. Complete the diagram to show how the presence of ligands around an isolated transition metal ion affect the energy of the d orbital. So in an octahedral complex, since the ligands are approaching between the actually along the axis, so the two orbitals along the axis are promoted to a higher energy level as compared to the three orbitals present between the axes. In a tetrahedral complex, the situation is reversed since the electrons of the ligands are approaching between the axes, so the three orbitals present between the axes are promoted to a higher energy level as compared to the two orbitals present along the axis. Labeling these orbitals, the ones having a set of two would be dx square, y square, and dz square on both sides, and the ones having a set of three would be dxy, dyz, and dxz on both sides. Now, the energy gap between the two sets of d orbitals for the octahedral complex would be labeled delta EO, and for the tetrahedral complex would be labeled delta ET. The O and the T is differentiating between the energy required for the octahedral complex transition as compared to the energy required for the tetrahedral complex transition. Question 7. Complete the electronic configuration of Cu and Cu2 plus. So copper has an atomic number of 29. So the electronic configuration for the 3D and the 4s for copper would be 3D10 and 4s2. When two electrons, actually not 310 4, it would be 310 4s1. It's 29, not 30. So 4s1. So for Cu2 plus ion, when the electron is removed from the 4s orbital and one from the 3D, we are left with an electronic configuration of 3D9. So four of the d orbitals will have pairs of electrons, and the last d orbital will have a single electron present. Next, the 3d orbitals in an isolated Cu2 plus ions are degenerate. Explain what is meant by the term degenerate in this context. Degenerate means all five 3d orbitals have the same energy present. It means they will not be split into two sets, which is the case when an octahedral or a tetrahedral complex forms. Complete the diagram to describe the splitting of the 3D orbital energy levels in an octahedral complex. So here we would have a split of with two orbitals in the higher set and three orbitals in the lower set. This is because the two orbitals in the higher set are the ones that are present along the axis, which are dx square y square orbital and the dz square orbitals, and the three orbitals that are below it are the ones that are located between the axes, which are dxy, dyz, and dxz orbitals. And the energy gap between these sets of d orbitals is labeled delta E O for an octahedral complex.